Because everything has some degree of complexity, everything will have an entropy. And we often use what are known as standard molar entropies for any given substance. These are entropies for a substance at a set of specific conditions, and we can also describe these as entropies of molecules or compounds in their standard state. And traditionally, these entropies are given in units of joules per mole Kelvin. And from the table on the right-hand side, you can see that standard entropies tend to increase with increasing molar mass, which is pretty expected. Increasing molar mass comes with increasing complexity and therefore increasing entropy. You can calculate standard molar entropies for different substances by comparing the change in heat capacity with the change in temperature. You can also calculate them a priori using quantum mechanical methods, but all of those are too complicated for us. For now, just know that other people have done the work, and we can use these values exactly like we've used tables of delta H's in the past. So an entropy change for a reaction can be estimated in a manner kind of analogous to that by which you estimate a delta H, which is the change in entropy is equal to the sum of the product entropies minus the sum of the reactant entropies. And as always, these values n and m represent just the coefficients for the various molecules in their balanced chemical equation. As I mentioned earlier, you can see that larger and more complex molecules have greater entropies. And at a fundamental level, this comes just from the fact that there are more particles that you have to keep track of, more different possible arrangements of those particles in space. So we can use our delta S expression to actually do some calculations. So if we want to calculate the standard entropy change for water splitting up into hydrogen and oxygen gas, we can do that by looking up in a table the standard molar entropies for liquid water, for gaseous H2, and gaseous O2. And at the end, we find that the delta S for this whole reaction is 326.3 joules per Kelvin. Please note that in this case, the units are joules per Kelvin and not joules per mole Kelvin. The mole has been removed from the expression because we use the molar coefficients. The other thing to note here is the sign of this value, and it's positive, and that implies that the entropy has increased as a result of the reaction, which makes sense. You went from liquid water, which is in a liquid state, which means it's relatively close together. Its freedom of movement is somewhat restricted. And you converted that into two different types of gases. So you went from 2 moles of water to 3 moles of various gases, and so you've increased the total number of molecules, and you've also changed from a fairly constrained state to a much more free-moving state in the gas.